Welcome to Chapter 6, Probability. We use the concept of probability all the time. We ask, for example, questions like, how likely is it that I'm going to get an A on this exam? What is the chance that the Chargers will beat the other team? What is the chance of rain today? These are all probability questions. But in everyday conversation, the answers are always kind of vague. Probably, might get an A on this exam. Chances are unlikely that the Chargers might beat the other team. With probability theory, however, we can offer far more precise answers, such as there's an 80% chance that the Chargers will win. There's a 70% chance that I will get an A on the test. There's a 30% chance that it will rain today. So that's what probability theory is all about. After this chapter, you will understand the definition of probability. You will be able to explain the assumptions of random sampling. You will be able to use the unit normal table to find probabilities, use the normal table to find scores for given proportions, and also find percentiles and percentile rank in a normal distribution. Remember the research process I showed you in the first lecture. Research begins with a question about an entire population. So, for example, does education lead to higher income, or are men more likely to experience a midlife crisis than women? So that's a question about an entire population. Actual research is conducted using a sample because we usually don't have enough time and money and resources to get the information from the entire population. Inferential statistics uses sample data to answer questions about the population. And with probability, we are able to determine what kind of samples we are getting from the population. So probability allows us to establish a relationship between samples and the population. Probability is a measure of how likely it is that a given event or behavior is going to happen. And there are several different outcomes possible. It is measured in terms of numbers between 0 and 1. So basically, if the probability is 0, right, it means that the event is never going to happen. If the probability is 1, it means that event is definitely going to happen. The closer it is to 0, the less likely it's going to happen. The closer the number is to 1, the more likely that this event is going to happen. Probability is mutually exclusive, meaning that two events cannot occur simultaneously, so they cannot happen at the same time. If there's a chance that A is going to happen, then B cannot happen. And the probability of any specific outcome is a fraction or a proportion of all possible outcomes. So based on this definition, this is then the formula to find probability. So the probability of A happening, so the event of A happening, is just the number of outcomes that are classified as A over the total number of possible outcomes. Let me show you an example of probability. Let's say I would give you this question that I usually give in Sociology 101. Which of the following men is generally known as the father of sociology? So he's actually the one that coined the term sociology. Let's say I would give you the possible answers: Karl Marx, Max Weber, Emil Durkheim, or Auguste Comte. So let's find out the probability of you getting the question correct. We know the probability of A, the probability of an event happening, so that this is the correct answer, is the number of outcomes classified as A over the total number of possible outcomes. Well, in this case, this just means the probability of getting it correct is 1 over 4. So we know one answer can be correct over 4 possible answers, because there are 4 choices. So it's 1 over 4. So the probability in this case is 0.25. If you would know for sure that it's not Karl Marx and you know for sure it's not Max Weber, so you would still be, is it Emil Durkheim or Auguste Comte, then you could eliminate those two, right? So now your probability of getting it correct increased, because now it's just 1 over 2 of 2 possible, because you would know for sure it's not Max Weber or Karl Marx. So now your probability just increased to 0.50. So the probability of any one event occurring is the number of possible ways it can occur divided by the total number of all possible events relating to that event. Let me give you another example. Let's say we're flipping a coin. What is the probability of getting tails? Again, by the formula of probability, it is the number of tails that are on the coin over the total number of possible outcomes. Well, we know we're looking for the probability of tails, and we know there's one tail and one head on a coin. So it is 1 on the coin number of tails over possible outcomes, right? Heads or tails. So it's 1 over 2. So the probability of getting tail is 0.5. And you can see the probability of getting heads is also 1 over 2, which is also 0.5. And then again, that adds up to 1, because you can only get tails or heads, because there's only 2 possible outcomes. How about the probability for playing cards? So let's say we shuffled a deck of 52 playing cards. What is the probability to draw a king when you randomly draw a single card? Probability of drawing a king. Again, thinking how many kings are there in a deck over the total number of cards in the deck. So we know that there are 4 kings, so the probability of getting a king is there are 4 possible kings over 52 playing cards. So your probability of drawing a king is 0.0769. How about the probability of drawing a heart? Again, how many hearts are in there? How many possible outcomes could there be? So the probability of hearts is there are 13 hearts, because we have 4 suits in there. 13 hearts divided by the total number of cards, 52, so the probability is 0.2500. Another example. Let's say we have a box with mixed marbles, right? All kinds of marbles in there. We mix them up really good. So we know that there are 300 marbles in total, and we know that there are 100 blue ones and 200 green marbles. So what is the probability of drawing a green marble? The probability of drawing green is 200 over the total number of marbles. We know there are 200 green ones and 300 the total. So that is 0.6667 is the probability of drawing a green marble. How about the probability of drawing a blue marble? Again, probability blue 100, because we know there are 100 blue ones in there, over the total number that are in there. 0.333 is the probability of drawing a blue marble. There are certain requirements for our definition of probability to be accurate. The process or procedure on how we draw the samples is what's called a random sample. It's the process that assures that each individual in the population has an equal chance of being selected, and that the probability of being selected stays constant from one selection to the next when more than one individual is selected. This requires sampling with replacement. So let me give you an example. If I would take a sample of 5 students from a classroom of 45 students, if I take the first student and I say, hey, come to the front of the board. He or she had a chance of 1 in 45 to be selected, because I had 45 students in my classroom. But now, if I would not replace that, the next student would now have a chance of 1 in 44, because one student is already at the front of the desk. And then the next student, so now let's say I get 1 more, then I have 2 students in the front. So now the next student has a chance of 1 in 43 to be selected. And that's not what random sample is all about. It requires sampling with replacement. So basically, when I get my first student who had a chance of 1 in 45 to be selected, I would have to throw him back into the classroom. So say, sit back down, and now I take my next random sample, and now it's 1 in 45 again. So in theory, the same person could be selected. That's what sampling with replacement means. Let's do a short learning check. Decide if each of the following statements is true or false. Choosing random individuals who walk by yields a random sample. So if I just pick a couple of people that walk by my classroom in the morning and say I take every 5th student, would that be a random sample? So please press pause. No, because not all individuals would walk by, so not all have an equal chance of being selected for the sample. The probability predicts what kind of population is likely to be obtained. Is that true or false? That is false, because the population is what's given, right? We do not have any influence over the population. The probability predicts what a sample is likely to be like. Practice this problem. Try to solve it by yourself. So please press pause. If there are 900 psychology majors at a university with 12,000 students, what is the probability that the next student who comes through the library door will be a psychology major? Probability of A, so being a psychology major, over the number of outcomes classified as A, over the total number of possible outcomes. So that just means the probability of being a psychology major is the 900 majors that are actually at this university over 12,000 total students. So the probability is 0.075. We said in the last chapters that the standard deviation is used to examine the way scores in a distribution are spread out and to compare the spread of two or more samples. We can, however, do much more with the standard deviation. With a single interval or ratio variable that we have reason to believe is normally distributed, we can make probability computations using the normal curve table. So we can use the normal curve as a probability distribution. Normal distributions are common shape, symmetrical. The highest frequency is in the middle, and then the frequencies taper off towards the extremes. It can be described by the proportions of an area contained in each section, and the z-scores are used to identify these sections. So the normal distribution follows a z-score transformation. Many research situations begin with a population that forms a normal distribution, and a random sample is then selected and receives a treatment, and then the probability is used to decide whether this treatment sample is noticeably different than the population from which it came. Sections on the left side of the distribution have the same area as corresponding sections on the right. Because z-scores define the sections, the proportions of area apply to any normal distribution regardless of the mean and regardless of the standard deviation. So this proportion, one standard deviation below the mean, is always going to be, this area is always going to be 0.3413, and the same, because it's exactly the same area, because it's symmetrical, above the mean is also going to be 0.3413. Two standard deviations below the mean is going to cover this entire area. So here you can see we have it in proportion in the middle, and then down here is the percentage of the total area. And you know that's just the proportion times 100. So this is going to be the proportion of 0.6826, proportion of 0.9444. So that's almost all of the people, right? Because if you have 95.44%, that's almost all of the people. But then if you go 3 standard deviations away from the mean in both directions, you catch almost 99.72, so almost everybody, right? And you just got this tiny little area left back here under both tails. So let's see how to apply this. If the question is, what is the probability of randomly selecting an individual from a population who has a SAT score greater than 700, and we know for the population distribution of SAT scores, which is normal distributed, that we have a mean of 500 and a standard deviation of 100. So what is the probability, when we know this about the population, of randomly selecting an individual from this population who has a SAT score greater than 700? Let's do a rough draft of what's going on in this problem. So we know this is what the normal distribution looks like. And in this case, we know that the mean is 500 and the standard deviation is 100. The question is, what is the probability of randomly selecting an individual from this population who has an SAT score greater than 700? So we're looking for x greater than 700. Well, if 500 is right here, right, we know that's the mean, then 700 is somewhere on this side over here. So let's say it's over here. So if we're looking for everybody that's greater, so the population that's greater, then we're looking for everybody that's in here, right? Everybody in here in this direction would be less than 700. Everybody between here and here would be between 500 and 700. So we're looking for P, probability of X being larger than 700. So we write down the C formula and then plug in 700 minus 500 over the standard deviation of 100 equals positive 2. So we get a C-score of positive 2. So now we have a C-score of 2, but how does that help us to find the proportion? Well, let's look at table B1, the unit normal table. This is in your book on page 571. So this is one of the tables we are going to be using a lot. So you can see that there we have the C-score in the first column, the proportion in the body in the second column, the third column is the proportion in the tail, and then the D column, or the last one, is the proportion between mean and Z. And you can also see the corresponding images on the top. So the body refers to the big part right here, and the tail is either above the mean, the tail's right here, and below the mean, the tail's right here. And then the proportion between mean and Z, which is column D, you can see the image right here. So let's find the proportion for our question where X is larger than 700. So again, we had a C-score of 2, and this is what it looked like. So we were looking for this proportion for everybody that was higher than 700. And we knew this came out to a C-score of 2, and we're looking for this proportion in the tail. So we have to go to the column C, and we see that the proportion is 0.0228. Let's do another practice. Find the proportion of the normal curve that corresponds to a C-score that's larger than 1.50. Please pause the video to solve this problem. Again, start with a rough draft. This is a normal curve distribution. We know that the mean is flat in the middle. We're looking for everything larger, the proportion larger than a C-score of 1.50. So that is definitely above the mean because it's a positive C-score. So it's somewhere over here. That's a C-score of 150. And the proportion larger than that is everything in this direction. So this is a visual of it. Now if you look at page 573, again, look at the normal curve distribution. So you always have to read this proportion from the table. We know we are talking about the tail. And here you can see that the probability is 0.0668. So D is the correct answer. Let's do another learning check to see if you understood the concept. Decide if each of the following statements is true or false. Is that true or false? For any negative C-score, the tail will be on the right-hand side. That is false, because for negative C-scores, the tail will always be on the left side. If you know the probability, you can find the corresponding C-score. Is that true or false? That is true. You just work backwards, right? You first find the proportion in the appropriate column, and then read the C-score for that column. When we look at the probabilities and proportions for normally distributed scores, we found that the probabilities given in the unit normal table will be accurate only for normally distributed scores, so the shape of the distribution should be verified before using it. And for normally distributed scores, we transform the x-scores or the values into c-scores and then look up the proportions corresponding to the c-score value. Let's do another example. What proportion of the normal distribution is contained in the tail beyond a c-score of negative 0.50? First, again, do a rough draft. So we know this is a normal distribution. This is where the mean is. We're looking at a z-score of negative 0.50, so it's on this side because it's below the mean. And we're looking for the proportion that is to this side. This is the visual. So now you look at the table, go to a z-score of 0.50. Remember, the negative just means it's below the mean. So you need to look on the left side. And again, we're talking about the proportion in the tail. So the proportion in tail you will see is 0.3085. You see that for all of these problems, you have to have the unit normal table. So these are not numbers you can memorize, right? Always look up the proportion in the table. And I showed you this earlier already, but you know that proportion can be easily converted to percentile, and percentile can easily be back converted to proportion by just multiplying by 100 or by dividing by 100. So percentile ranks is just the percentage of individual in the distribution who have scores that are less than or equal to the specific score. And probability questions can very easily be rephrased as percentile rank questions. So let me give you a few examples. For a normal distribution, what z-score separates the top 10% from the remainder of the distribution? Practice this problem. Try to solve it by yourself. So please press pause. So again, begin by making a rough draft. We know this is our normal distribution. We know each side has 50%. Altogether, we have 100. So if we're talking about the top 10%, then this is going to be the top right here. So that means 90% are right here, and 10% are the top ones. Well, if we know it's 10%, we know that's a proportion of 0.1000 that are in this side of the tail. So now you just have to look at the table and look for a proportion in the tail of about 0.1000. And you'll see that you're not going to find exactly the value. The closest one is, you're going to see in the tail a proportion of 0.1003, and that corresponds to a z-score of 1.28. So you can see once we know a proportion, or we know a percentage of area we're looking for in the normal distribution, we can find very easily the corresponding z-score. For a normal distribution, what z-score values form the boundaries that separate the middle 60% of the distribution from the rest of the scores? So please press pause. So first, let's do the rough draft. This is the normal distribution. The middle 60% of the distribution be about here, 30% on this side and 30% on this side. That's the middle 60% of the distribution. And we're looking for the corresponding z-score. So the first thing you have to do is look at the table and look for between the mean and z when the area is 0.3000. And you'll see that's column D. There you see that the closest one is 0.2995 and the z-score is 0.84. Now we're looking for both z-scores because it's asking for the z-score values that form both of these boundaries, so that it's negative and positive 0.84. In summary, the probability of a particular event A is defined as a fraction or proportion. So the probability is the number of outcomes, in this case classified as A for the probability of A, over the total number of possible outcomes. All probability problems can be restated as proportion problems. So the probability of selecting, for example, a king from a deck of cards is the same as saying the proportion of the deck that consists of kings. So for frequency distributions, probability questions can be answered by determining the proportions of the area. For normal distributions, probabilities or proportions can be found in the unit normal table. The table provides a listing of the proportions of a normal distribution that corresponds to each of the z-score values. And with the table, it's also possible to move between the x values and the probabilities using the two-step procedure of using the z-score formula that allows you to transform x to z or to change it back. And the unit normal table allows you to look up the probability or the proportions corresponding to each z-score. And percentiles and percentile rings measure the relative standing of a score within a distribution. Percentile rank is the percentage of individuals with scores at or below a particular X value. And a percentile is an X value that is identified by its rank. The percentile rank always corresponds to the proportion to the left of the score in question. Congratulations, you reached the end of this chapter. Remember, if you have any questions, please email me anytime. Bye. See you next time. Congratulations, you reached the end of this chapter. Remember, if you have any questions, please email me anytime. Bye. See you next time.